Now we're going to look at a different factorization pattern. The first set of factorization patterns that we looked at were factoring out monomials. And I want to keep a comprehensive plan in mind. Factoring is one of those concepts where you break it down into small pieces and then try to bring it back together and put all the pieces together so you have a comprehensive plan of what you want to do. But what I want you to keep in mind, in your comprehensive plan, the first thing you're always going to look for is the greatest common factor. You're going to look for that monomial factor. That should always come first and foremost in your mind. That's not going to happen in these examples. Like I said, it's one of these concepts where you break it down into small parts and you put it back together. So we're breaking it down into a different type of factorization process. So the first thing we're looking for is greatest common factor. If we don't see one, then we've got to have another strategy or another strategy to go to. So now we're going to look at the second part of this. The second part is you got to look for some very specific things. Number one, is it a difference of two, and I call them perfect squares? Okay, so is this polynomial that you're looking at a difference of two perfect squares? Which means if it's a difference of two perfect squares, all you're going to be looking at is a binomial. Now that's not the situation we're going to be looking at in these next two examples, because you can clearly see that the next two examples that we have, both of these are trinomials, so they're not binomials. So it's not part of this. This is this part where we're going to break it down into smaller pieces and then put it back together. But I'm going to be looking for some of these things as we go through and trying to build an entire picture. So one is your GCF. Step two, do you have a difference of two perfect squares? If you don't have a difference of two perfect squares, then step three, do you have a trinomial? And if you have a trinomial, then you've got to always try to figure out if it's a trinomial, they factor into two different binomials. So now we're going to look at binomial factorization. Okay, so let's dive into example number 2 here, where I've got question 5. It says we have y squared plus 12y plus 27. So I first have to examine these three elements, these three members of the polynomial. Is there a greatest common factor that I can find in these? Can I take a y out of all three? That's negative. I can't. There's two terms, but I can't take it all three. So I need to find something that goes into all three terms. So I can't take a y out of all three terms, and I need to see if I can take out numbers. Is there any greatest common factor between a 1, a 12, and a 27? The only common factor that these numbers have are 1, and if you factor out a 1, it does nothing to change your polynomial. So if all they have is a greatest common factor of 1, then I know I don't have to worry about a monomial factor. So what I've done is I've eliminated the possibility of the factorization strategy of a greatest common factor. Move on to another strategy. Greatest common factor isn't going to work. So here's where we get into our second strategy. I'm going to look at this expression, this polynomial, and this polynomial is a trinomial. So as soon as it's a trinomial, I know I don't have a difference of two perfect squares, so that's out of the mix. So now I got to figure out all trinomials, if factorable, will factor into two binomials. So this is our double distributive property, or our FOIL, being reversed. So again, every time you factor, you're reversing the distributive property. And the FOIL reverses the distributive property in essence, even though the distributive property is also used to represent factoring. So okay, here's our strategy. Remember when we did FOIL, whenever you had two binomials, the things that were sitting here and here in these first locations had to be multiplied together. So this y squared has to be your first. So when I multiply this member here times this member here, I've got to get a y squared. Well, that really forces it to be a y times a y. So in my first terms, I got to have a y times y. Also in FOIL, and we kind of do this in a little different order because now I'm going to go to this last term back here. If I think about that, the number sitting here in the last two terms of our binomial, when we multiply those last ones together, the L, that has to give us 27. Now that gives us a very limited number of possibilities, because when I multiply two numbers together, I got to get 27. So now I'm going to be thinking about 27. How can I multiply two numbers together to get 27? Well, one way I could do it is 1 times 27 Another way I could do it is 3 times 9, and I think those are my only options that I have. So I could try one of those combinations, either a 1 and 27 or a 3 and 9. Those are the only things that I can use in these last two positions. So I've got to find the right combination that's going to give me, and this 12 that I'm going to look at here, that is your outside inside. So once I place these numbers, either the 1 and 27 or the 3 and 9, I've got options here. I've got to figure out what option is the best that will make that 12y. I'm going to put those in here, and then I got to check the outermost two and the innermost two, the outside, inside, and make sure I can get a positive 12. So realistically, I already see what I need to have happen here. If I take a 9 and a 3 and I add them together, I'm going to get a 12. So what I'm going to do is I'm going to put a 3 here and a 9 there. I can reverse them. And I also know that my signs have to be positive because that last sign is positive. And my middle sign is positive, so plus, plus. Now, I'm hoping that I'm hitting some things that you remember here. Let me come back to this sign that I was just talking about. Anytime I need to figure out what my signs are in my binomial, these things that I'm highlighting here, I isolate right here first of all. If that is positive, then the signs have to be the same. And I look to the middle sign here. If it's positive, then they're both going to be plus plus. If this sign is positive, but this middle sign, for instance, if I change it to a negative, then this has to be minus minus in these locations here and here. So hopefully that's something that you kind of remember. If not, we're going to go through some more examples and solidify that idea. So what I'm left with is a factorization of y plus 3 times y plus 9. If I check this to make sure I'm right, if I do the first terms, I got y times y, which is y squared. If I do the outermost two, that's 9 times y, or 9y. If I do the innermost two, that's 3 times y, or 3y. If I do the last terms of my factorization, it's 3 times 9, which is a positive 27. Our like terms, 9 and 3, are collected into 12y, and that's how I know I have the correct factorization. I recheck it with the distributive property. So there's the first go around of factoring a trinomial into binomials. So here's what I want to get across. Get to your greatest common factor. If that doesn't work, is it a binomial? If it's not a binomial, trinomials factor into binomials. So let's speed that process up in the second example I have here. Number 1, do I have a GCF? Is the greatest common factor in any of these three? There's not a y in all three. Can't take out a y. There's no common factor between a 1, 5, and 4. As a matter of fact, anytime this is a 1, there will not be a greatest common factor. So step number 1 is done. Step number 2, is it a binomial? Nope, I can clearly see it's a trinomial, so I don't have to worry about the difference of two squares. So forget about the factorization of difference of two perfect squares. Number 3, is it a trinomial? You bet it is. And every time I have a trinomial, try to spell that right, I know it's going to factor into two binomials. So I immediately start partitioning this. I got the y squared minus 5y plus 4. Trinomials, if factorable, will factor into two binomials. So I know this is my first term. This has to be a combination of my inside and outside, and this has to be a combination of my last term. The first terms multiplied together have to give me a y squared. So that pretty much solidifies. This must be a y and a y. I'm going to look at this sign here. If that sign is positive, I know my signs are the same. Every time that is positive, my signs will have to be the same in here and here. Now I simply look to the middle sign here. If it's negative, then I simply mimic this negative, negative. Okay, so I know my signs in there are negative, negative. Now my last term is a 4, which means if I'm starting to eyeball these last two spots in my binomials, when I multiply these two together, it's got to give me a 4. So I need to think of 4, and what are the factors of 4? Well, I can go 1 times 4, I can do 2 times 2. So one of these combinations is going to give me, for the outside, inside, a negative 5. So because these signs are the same, negative, negative, when I do this, outermost 2, and this, the innermost 2, since they're both negative, I'll end up adding them. So I'm going to add a 1 and a 4, and 1 plus 4 is 5. So I'm going to have a negative 1 and a negative 4. Now if I double check all this, I should be able to get back to what I started with before I factored. So to get back to what I had before I factored, I used my distributive property. So double distribute. We got our y times y, which is y squared. We got our outermost, which is negative 4 times y, which is negative 4y. We got the innermost two that have to multiply together, which is a negative 1 times y, or a negative 1y. Then you got a negative 1 times a negative 4, so when you do a negative times negative, it's positive 4. So then we collect our like terms, y squared minus 5y plus 4. And is that what we started with? If it is, we have the correct factorization. Yahtzee. So that's the factoring of trinomials into two binomials.